Hello everyone, welcome back to Chapter 4. We're going to try to finish up the chapter today with the final topic of relative motion. And with relative motion, what we're really going to do is relate how the motion of objects can be measured from different frames of reference. And then we can actually take that idea much further into the area of relativity, which is its own physics course, but it's more focused on the idea of the object approaching the speed of light and how our ability to perceive those measurements is affected. But we're not going to dive that deep into the subject in this course. But at the very least, we'll be able to show how an object measured in one reference frame can then be converted to the measurements of a separate reference frame. So what we'll do is we'll set up a reference frame, basic XY axes, and out in space here we'll have a particle, call that particle P. And if I want to measure the position of that particle with respect to the origin of this established reference frame, then I just draw a line from the origin out to where our point exists. So I now have a vector that describes the position of that particle. Now if I want to allow that particle to move, I can displace it from one location to another. I can then time that displacement to describe its velocity. And if the velocity is changing, I can then measure that change in velocity as an acceleration expression. So everything that we've done so far in terms of the kinematics, the definitions, everything is still there. It is in a two-dimensional reference frame, but we're prepared to handle that now with our discussions on vectors and two-dimensional kinematics. But now we want to see what happens to all of those measurements if we use a different frame of reference. So I'm going to call this frame A. As such, we have the position of particle A measured with respect to frame A. So I'm going to use R. Try to clean that up a little bit. So we're going to use R as the two-dimensional position vector, but it's measuring point P with respect to frame A. So that's what our subscripts are for. Then we're going to introduce a different reference frame. So someone else comes along and they want to measure everything in the system with respect to their reference frame, which we will call frame B. And there's really not a whole lot different about these two reference frames, except where their origins are located. I made this example pretty straightforward in having both the x and the y axes running parallel to each other, but we just as easily could have rotated one of those reference frames. But for an introductory discussion, this will serve our purposes quite well. And so now I want to measure the position of that same point in space, but from a different frame of reference, I get a different vector. We'll call this R of PB. So this is the position vector of point P as measured with respect to frame B. And just like with frame A, I can measure the displacement of our particle with respect to frame B. I can then measure things like velocity, acceleration, etc. But because I have a different starting point with my origins in the frames of reference, I'm going to get different numbers for those measures. And so what we need to do is we need to figure out how can we take the position of that point out in space and relate it to the two different reference frames that we're using, such that we know that we're measuring the same physical point out in space. And the way we're going to do that is we're going to introduce a third vector, which is drawn from one reference frame origin to the other. And I will call this vector the position of frame A with respect to frame B. So we are measuring the origin of frame A with respect to the origin of frame B. Now what we have is essentially a vector addition problem. If I start at the origin of frame B and I travel up the vector RAB, that gets me to the origin of frame A, and then I can follow the vector RPA out to point P. So by adding those two vectors together, and you'll notice we've added those head to tail, that's a vector addition problem, and we know how to handle vector addition. The result of adding those two vectors together is the vector RPB. And we can now write that out as a vector addition problem, because now we can see that by adding together these two vectors, we will get from the same start point to the same end point, regardless of which path we take. So we'll back this up, clean this up a little bit. So this is how our relative motion is going to work. We have a vector addition problem that essentially allows us to transition from one reference frame to another when it comes to measuring the same point out in space. And the way that we do that transition is right here, by knowing where the two reference frames are in relation to each other. So now what we can do, and the math is actually going to go pretty quick now, because we already have all of the definitions that we need for things like position, displacement, velocity. So what we have here is an expression for, sorry, I'll try that again, for relative position. Where we can measure the position of point P relative to either reference frame. Now, we're going to carry this word down all the way, so everything gets relative placed in front of it, and the next term that comes after position is displacement. And if you remember, back in chapter 2, we defined displacement as the change in position. Now for just one axis, that change in position would be the change in final minus initial for the x direction, Likewise, we would have final minus initial for the y direction. If there was a z direction, we could have that as well. But then all of these would fit together to produce a vector in either 2 dimensions or 3 dimensions, depending on how many axes we happen to be working in. And we can take all of those differences and combine them into a 3-dimensional displacement vector that we would call delta r. So back to the picture, if I were to take this point P and move it through space, maybe I should pick slightly different. We'll move it up here. So this is the initial position of our point. This will be the final position of our point. Well, in doing so, to measure the final position of that point with respect to the 2 reference frames, I would then have to redraw the vectors with respect to their reference frames, and I would still get a relative position expression similar to what we have here, only now it's describing the final position of that particle. But that final position of the particle is going to be described by the same change in x and y components. I need to change back to my color here. So we started at P naught, and then we moved back to P final. Okay, well, P final is going to require a displacement of so many units in the y direction and so many units in the x direction. But those same values can be shown using the difference in the vectors that are drawn from either the A reference frame or the B reference frame. The only thing that doesn't change during this displacement is the definition of how our reference frames move. Because right now we're assuming that our reference frames are locked in place. So what we can do to sort of fast forward is we can say that our point P has displaced itself through space, and we can measure that displacement from the B reference frame. But that same point has displaced itself in the A reference frame. And the way that we're going to describe the displacement is to know whether or not there was any displacement between the 2 frames of reference themselves. And right now we're saying no, the frames are going to remain in constant position with respect to each other, so we can say, well, that change in position is 0. The reference frames did not move with respect to each other. But if that's the case, then that means that the change in position for the particle has to be the same regardless of what frame of reference we used to describe that displacement. And that much is true. If we completely eliminate those frames of reference from the diagram and we just look at this particle as it moves from one point in space to another, well, does that displacement change just because we chose to measure it from one reference frame or another? And physically, the answer is no. There is no change. The only thing that might cause a change is if one of those reference frames was in fact moving. So what we're going to do now for additional discussion on this topic is we want to keep this expression as general as possible, and that means that we're not necessarily going to assume that this has to be 0. In fact, we're going to go ahead and assume that one of those reference frames could be moving. And if that's the case, the next definition in line after displacement would be velocity. So as this particle has moved through space, if we time the displacement, we will get velocity. But now we can actually kind of abandon the whole diagram approach, and we can just let the physics and the math take over. Because we know that velocity in the 2D and the 3D sense is any change in position with respect to time. Well, this expression that we have right here has already taken care of the change in position that is happening within our system. All we need to do is go through and divide everything by time, and we will automatically get an expression that describes the velocity in the system. Well, we're going to, actually I don't want to put that as an equal sign just yet. So velocity will be the change in position with respect to time. But we're gonna carry through with all the notation here. All right, so every one of these terms that we just divided by time is going to turn into a velocity term. But what about the subscripts? Well, those subscripts are just going to come along for the ride. For this first term, I'm looking at how the point in space displaces as it's measured with respect to the B reference frame. And so this expression is going to tell me how that particle moves with respect to the B reference frame. Likewise, for the other two terms, we are again going to produce velocity expressions, but the second term is going to tell me how the velocity of frame A is measured with respect to frame B. So now we're assuming that one of those two reference frames up here is moving. And in this case, it's going to be reference frame A that is moving with respect to frame B. Now we'll go ahead and finish up this expression, and then we'll talk about what it means to have one frame of reference moving with respect to another. But this last term is going to be the velocity of point P measured with respect to frame A. And so if you notice as we step down through all of these expressions, the arrangement of these subscripts is consistent. The only thing that we're doing is we're progressing through the definitions of position, displacement, velocity, etc. And so then obviously the next the next term in line would be relative acceleration. And now you can probably guess how we're going to produce a relative acceleration expression. And that is that, oops, I don't know why I had a D over here, sorry. There are two types of relative velocities. I guess we'll come back and talk about that. We'll go ahead and get our expression for relative acceleration first. But so our definition of acceleration is a change in velocity with respect to time. So just like we did for the velocities, we're going to look at how these velocities change with respect to time. And so just like the changing position, every one of these terms can have a changing value. If our point changes its velocity with respect to the B reference frame, if our A frame changes its velocity with respect to the B frame, and if our point changes its velocity with respect to the A frame. If we then measure all of those with respect to time, we now have acceleration expressions. And so our acceleration, again, that's not an equal sign, sorry. Our accelerations are going to be acceleration particle with respect to B frame, acceleration A frame with respect to B frame. So this term right here is assuming that one frame of reference is accelerating with respect to another. And then we have acceleration of point P with respect to frame A. Alright, so we've got all of our terms here, but a couple minutes ago I mentioned that there were two types of relative velocities. There are also going to be two types of relative acceleration. And the reason for that is the same reason why we had two different velocity terms back in our original derivation. And that is because whenever you have delta t, remember delta t can be too big, and so every one of these terms that is using a large time interval would have to be considered an average. And so every one of these terms would have to be considered as an average velocity. But I could very easily turn all of those into instantaneous expressions if I were to shrink those time intervals down to something infinitesimal. So instead of having deltas in all of those statements, I'm just going to write out the first statement from that expression. Instead of having the deltas, we would have our differential statements for everything. And so these would turn everything that we have into instantaneous measures. Likewise for the accelerations. If we use a delta t that is too big, then all of these acceleration terms, the best that we're going to be able to get out of them are averages. And so we would have to write them as such. So these subscripts are kind of getting out of control here. But just like with the velocities, if we can shrink those time intervals down to something instantaneous, then those differential terms will come in. They will replace the deltas, and we will have an instantaneous expression. Okay, so we've got all of these expressions here that tell us what the process is for measuring relative motion. And these equations are all well and good, but they're not really going to do much good to us if we don't know how to use them in the physics. So what we're going to do, we're going to try an example problem with relative velocity. So that would be this expression right here. And we're gonna try a problem that most everyone has done at some point. You're driving down the interstate, and you have a velocity of, we'll say, 75 miles per hour. Now, usually in a physics problem, we would use metric, but up here, all we're doing is we're adding and subtracting terms, the same terms. So whatever addition or subtraction we get will be in the same units that we start with. So you, the student, so we'll say velocity of student, you're traveling down the interstate at 75 miles an hour, and then all of a sudden there is a police car which comes screaming past you at 100 miles per hour. So the velocity of the police car is 100 miles per hour. And you're both traveling in the same direction. And what I want to know is, what is the velocity of the police car with respect to your car? And so you look at that and you go, oh, it's 25 miles per hour. And I would say, well, how did you know that? How did you do that so fast? You'd say, well, I just took the velocity of the police car and I subtracted my own, and the difference between the two was 25. Okay, but in the relative velocity expression that we have, actually, before I make anybody confused here, let's change the subscript of the police car to C. So we'll call this cop car. Velocity of cop car with respect to student, because I don't want to get that confused with the subscripts that we have up here. Up here, P was for the point that was moving. Alright, so I'm going to bring that equation down here. Velocity PB equals velocity AB plus velocity PA. So this is the relative velocity expression that we derived up above. And I want to see how we can apply this expression to the system that we have in front of us, and still get the answer that you got by doing some basic arithmetic in your head. You said that you were going to take the velocity of the cop, subtract your own, and you get the 25 miles per hour. Okay, well, there's no subtraction in this equation unless we shuffle some things around. In addition, every one of these terms has two subscripts in it, and well, that term only has one subscript, that term only has one subscript, yet we're producing a value that has two subscripts. So this means there must be a third subscript somewhere. It's hiding. What is it going to be? And if we look at our our default expression here, we currently have 3 different subscripts. We have P, which is the point that was moving around in our frame of reference. I'm going to call this the point of interest. So this is going to be whatever it is that we're looking at in the system. It's what we want to measure. And then A and B were the 2 different frames of reference. So this is frame A, and this is frame B. So there have to be 2 frames of reference in any of these problems that we do. So the question is, what are we looking at? What is holding our interest? And for this particular problem, it is the COP. So anywhere where I have the subscript of P, I am going to replace it with the subscript of C for the COP. And that only leaves us with 2 frames of reference. So I guess that means that you, as the student, as you look at the COP driving past you, you are a frame of reference. You are measuring from your changing position how fast the COP car is moving. And so I'm going to go ahead and say that you, the student, have become the first frame of reference. And so anywhere where we had A as a subscript, we're now going to replace that with S for student. But what about frame B? What is frame B? If we go back up to the very first picture that we had for these frames of reference, you are now frame A. And frame A is moving. But what are you moving with respect to? And that question can be answered right here. You say that your speed is 75 miles per hour. Well, 75 miles per hour with respect to what? How fast are you moving with respect to what? Well, typically when they take those speed limit signs, where do they stick them? They stick them in the ground. And so those speed limit signs say that you can only go so fast with respect to the ground as your reference. And so that is going to be our second reference frame. So anywhere where there was a B, I'm going to replace it with a G. So here we go. We're going to take our default relative velocity equation and we're going to rewrite it for the new subscripts. So V sub PB is now going to be V sub CG. V sub AB is now going to be V sub SG plus V sub PA. PA now becomes CS. All right, so as we go through here, what does this mean? Well, this is the velocity of the COP with respect to the ground. How fast was the COP going with respect to the ground? Well, that's this value right here. So let's go ahead and sneak in those extra subscripts there. Both of these are measured with respect to the ground. That is 100. Here we have velocity of you, the student, with respect to the ground. That was 75. And the last one is the velocity of the COP with respect to the student, which is what you measured up top. Well, what would that value have to be in order to make a true statement? Well, we would have to take the velocity of the COP with respect to the ground and subtract the velocity of the student with respect to the ground. And oh, that's exactly what you did up above about 10 minutes ago. But now we can see that the physics is actually doing exactly what you did in your head. You took the difference of the two values, whereas the setup for the problem is actually doing a combination or an addition of two terms as opposed to a subtraction. And so, well, it looks like the problem's over, but we could ask some other questions, like we just found what was the velocity of the cop with respect to the student. Well, what would the velocity of the student with respect to the cop be? So we already know that this was 25 miles per hour. So what would the velocity of the student with respect to the cop be? So what have we done here? Well, we've essentially changed reference frames. We're no longer looking at the cop car, we're looking at the student's car. So to make this work, we need to update the subscripts that we're using in our equation. So remember the point of interest. What is it that you're looking at? What is it that you want to measure? Well, we want to measure the velocity of the student with respect to the cop car. So with respect to, that should be an indicator to you that the next item in line is going to be a reference frame. So everywhere where we had the S and the C, those are now going to be interchanged. But we're still gonna use our default expression here to show us what needs to go where. So now anywhere where there was a P, it's going to be replaced with an S. So we had an S here, we had an S here. A is going to be replaced with a C. So there was an A here, now there's a C. And B is still the ground reference frame, so we can still do G and G. And I want this value right here. So we can find that by taking the difference in the student's velocity with respect to the cop's velocity. Now these two values, they haven't changed. We still have 75 and 100, but now you can see that instead of getting 25 miles per hour, we're getting a negative 25 miles per hour. Well, why a negative? Well, that's because you are now the cop. And as you travel forward, as you pass the student's car looks like it's moving backwards with respect to you. In other words, the student's car falls behind you as you move forward. Well, so what else could we do with this? This was basically a one-dimensional problem because everything that we had was moving along a one-dimensional axis. I should have put that X in there earlier. But now we should consider what happens in 2 dimensions. So for this next example, let's take 2 planes that are taking off from the same airport. Plane number 1 will take off and it will have a velocity of we'll say 250 miles per hour, 30 degrees north of east. And plane 2 will have a velocity of 300 miles per hour to the southwest. And I would like to know what is the velocity of plane 1 with respect to plane 2. If it helps, go ahead and draw the vectors. So our XY axes have now been replaced with the appropriate compass directions. And velocity 1 is 250 at an angle of 30 degrees north of the easterly direction. So we have to measure 30 degrees to the north. 30 degrees to the north of east. And then we can put in velocity 1. 30 degrees and 200 miles per hour for the magnitude. So there goes plane 1, and then plane 2 is 300 miles an hour in a direction southwest. Now there are no angles given. All we're told is southwest. But that would imply that we have equal parts south and equal parts west for the motion. And the only way that that's going to happen is with a 45-degree angle. So 300 miles per hour to the southwest. So these two planes look like they're almost pulling directly away from each other, but that's not quite the case because they're not 180 degrees apart. So what we need to do to figure out the relative velocity between these two planes, we can think of this the same way as what we did with the cop car problem. We can take the difference in the two velocities, but which velocity do we subtract from which? And just keep in mind the way that this is written. We want the velocity of plane 1. Stop. Plane 1 is what we're interested in. Plane 1 is what we're looking at. So our point of interest is plane 1. What are we measuring with respect to? We're measuring with respect to plane 2. Plane 2 just became the first reference frame in our problem. So what's the second reference frame? Well, go back and ask yourself, how are these velocities being measured? What are they being measured with respect to? Well, maybe they're measured with respect to the airport that they left. And that airport is fixed in place. It's on the ground. Oh, there we go, ground. Each of these velocities is being measured with respect to the ground. There's our second reference frame. So we'll go back up and we'll grab that relative velocity equation again. V of PB equals V of AB plus V of PA. And we're just going to rewrite the subscripts for what we have in this problem statement. So velocity of plane 1 with respect to the ground will equal velocity of plane 2 with respect to the ground plus velocity of plane 1 with respect to plane 2. We want velocity of plane 1 with respect to plane 2, so we will take the difference in our ground-based velocities. And now we can kind of see what the order should have been. We're using plane 2 as a reference frame. So stick yourself on plane 2. You're the reference frame, you're the one that has to do all of the measuring, and you have to look this way to see plane 1 moving away from you. So just like the cop car, you would take their velocity and subtract your own from it, and you'll get the relative velocity. Okay, well that's the toughest part, believe it or not, because now, even though we have a two-dimensional system in front of us, remember that we're not really in the habit of doing our vector problems all at once. It's a whole lot easier if we can take these problems and break them down into just x and y directions. So if I can see how plane 1 and plane 2 are moving with respect to each other just along the x-axis, then I can get the x component of their relative velocity. And if I can see how these planes are moving with respect to the y-axis, then I can get the y component of their relative velocity. And then we can put those components together to tell us what the magnitude and angle of that relative velocity need to be. All right, we have our game plan essentially. Now we just need to find out what are these values so that we can combine them. And now is where our picture will come in handy. Our velocity of plane 1 with respect to the ground has components in the north and east directions. So right here we have v1gx, here we have v1gy. And the x component, that is the leg that is adjacent to our angle, so we will have 200 cosine of 30. The y component, that is the leg that is opposite of our angle, so we have 200 sine of 30. Calculator time, 200 sine of 30 is just 100. And units are still there. And we have 200 times the cosine of 30, which is about 173.2 miles per hour. Right, so I'm just going to write those components out right here. We had the x component was 173.2, the y component was 100, and now velocity 2 with respect to g. So over here we've got velocity 2 with respect to g. And because we have a 45-degree angle, both the x and y components of this vector are going to have the same magnitude. And as it turns out, they're both pointing in the negative directions with respect to positive x and y. So each of these will have a value of It doesn't matter if we use sine or cosine. I'll just use cosine. We've got 300 cosine of 45, which is 212 miles per hour. So we have 212 miles per hour to the negative x direction, so I'll just call that negative 212. And we have a negative 212 in the y direction. Negative 212, negative 212. And so now, well, how are we going to get the components of our vector? Well, we need to take the components of vector 1, subtract the components of vector 2. Well, that's exactly what I'm ready to do here. I just have everything stacked up in column form. So we have v1g minus v2g. So I need to subtract this second line from the top line. We now have 173 minus a negative 212. And this is going to give us 385.2 and a 313. And both of those came out positive. So why is that? Well, remember, you're sitting in a seat on plane 2, traveling to the southwest, and you're looking at plane 1. And as you look at plane 1, so this is your line of sight as you look at plane 1. This is the velocity of plane 1 with respect to plane 2. And now if you look at the components that this vector has along the x and the y directions, well, those are pretty big components, and each of them is in excess of about 300 miles an hour, and they're both pointing in the positive directions, respectively. And so looking at plane 1 from plane 2, plane 1 looks like it's really just screaming away from plane 2. And so now we can take our square root of the sum of the squares to find the magnitude of this relative velocity. So we have 385.2, we need to square that, add it to 313 squared, take a square root, and I'm getting approximately 496 miles per hour. So these two planes are pulling away from each other at a rate of almost 500 miles an hour. And the last thing we might want to try is to find the angle that our relative velocity vector is pointing at. Well, we can do that by using the components of our relative velocity vector. We have 313 over 385, y component over x component. 313 divided by 385, and then we need an inverse tangent of that. And I'm getting right about 39 degrees. Well, 39 degrees with respect to what? Well, with respect to the point of reference, which is you. You are on plane 2. You are the one looking at plane 1. You are the point of reference where everything is being measured with respect to. And I've mentioned in previous videos, when you are using your inverse tangent, keep an eye on what ends up in the denominator, because that is where you will need to measure your angles with respect to. Well, the denominator was the x component of our relative velocity vector, v12. And so that x component is pointing in the positive x direction. Was that? Sorry, 39 degrees. So from your point of view, from your perspective, plane 1 is traveling away from you at a speed of approximately 500 miles an hour, 39 degrees north of the easterly direction. And that is how our relative velocity is going to work in 2 dimensions. We can take this a little bit further. There are some basic real-world questions that we could ask. If v12, and I'm just going to round this up, if v12 is 500 miles per hour at 39 degrees north of east, how long until the 2 planes are 1,200 miles apart from each other? So we know that plane, or I think I was calling them plane A and B, I'm sorry, plane 1 and 2. We know that plane 2 is headed off this way. We know that plane 1 is sort of headed off this way. But as the 2 pull away from each other, the relative velocity between the 2 is fixed. And so what we need to do is we need to figure out, as we travel at a rate of 500 miles per hour, how long is it going to take to cover a distance of 1,200 miles? Well, that becomes a pretty basic arithmetic expression. Miles per hour is a measure of velocity, and velocity is a measure of displacement over time. Technically I used delta x there. I should have used delta r. But our delta r is going to be the 1,200 miles of separation distance. And we're looking for the time that it takes to cover that distance at a rate of 500 miles per hour. So we can just switch around the 1,200, the 500, and the delta t, and now we have our answer. It's going to take us approximately 2.4 hours for these planes to pull away from each other a distance of 1,200 miles. Another question that we could ask, now that we know what the velocity of plane 1 with respect to plane 2 is, what is the velocity of plane 2 with respect to plane 1? So I've just switched the two the two subscripts around. But let's go back to this picture that we had up here, and I'll clean it up again. If we are on plane 2, looking at plane 1 as it travels away from us, that's the velocity v12. That's what we've already calculated. But now you magically transport yourself so that you're now sitting on plane 1. And you're looking at plane 2. Well, you're going to use the same line of sight. Now you're going to be looking this way. And so, how fast is plane 2 going to be pulling away from plane 1? Well, it's going to be the same magnitude of velocity. The only difference is the angle that we're going to use to measure that. What is this angle going to be with respect to plane 1? Well, we had 39 degrees here, and so if we translate ourselves up to where plane 1 is at, I can actually use some geometry again. The x-axes that I have here are parallel lines, and opposite angles of lines that intercept parallels are equal to each other, and so I can say that v21 is 500 miles per hour at 39 degrees south of west. Well, that's the magnitude and angle, but how would this affect the components? What would the components of vector 2, 1 be? Well, it's pretty obvious now. All we've done is we've shown that these two vectors are equal and opposite to each other in every respect. And so if I were to now draw the x and y components of vector 2, 1, I would see that they're exactly the same values as what we had for vector 1, 2. They would just have minus signs on them now because we've flipped ourselves over 180 degrees, quite literally. So do keep an eye on how those subscripts are written out, because they could very well mean the difference between a positive and a negative on your components. But now you can put these together if you want into your Pythagorean theorem. Again, square root of the sum of the squares will result with a 500 for magnitude. And then if we put these numbers into our inverse tangent, we will again get a 39-degree angle, but because we now have a negative x component, we would have to measure from the negative x-axis, which is technically west, and we have to measure to the south of west. Exactly what we had there. Alright, I think that's enough for relative velocity. We're not actually going to do a whole lot with relative velocity in the remainder of the course, but for future coursework, especially in some of your engineering courses, you may very well end up having to convert measurements from one frame of reference to another, and so this is going to be the starting platform as to how we would accomplish that. So when we get back, we will start Chapter 5. Have a good one.